Hello and namaste, respected judges. This is Aditya Bhalera from Team Slayers. Today, I would like to begin with one of the greatest engineering achievements in human history, the Apollo 11 case study. On July 20, 1969, during the Apollo 11 lunar landing, the Apollo Guidance Computer (AGC) suddenly began displaying 1201 and 1202 alarms due to system overload. The computer detected the problem, but it could not explain what was happening and whether its guidance could be still trusted or not. At the same time, the spacecraft was heading towards a hazardous boulder field with less than a minute of fuel remaining. Confronting uncertainty and limited information, Neil Armstrong took manual control and safely landed the lunar module. The mission succeeded, but it exposed a fundamental challenge. Future AI systems must understand uncertainty, reason through it, and explain their decisions in a way humans can trust. That is exactly what our project aims to build. Thus, introducing Symbiosis. Synchronous multimodal belief integration with orbital self-interpretability system. See, the idea is simple. Instead of building isolated AI systems, we synchronize perception, reasoning, uncertainty estimation, simulation, and explainability into one unified architecture. Now let's go to the dashboard. So this is how the dashboard looks like. Let's initiate the mission and boom, this is the dashboard that you can see over here. The system is composed of 5 operating AI agents. First is perception agent, second is cognition agent, third is action agent, fourth one is orchestrator consensus, and fifth one is conversational AI agent. These 5 agents work together in order to ensure the safety for the spacecraft. Now let's talk in detail about perception agent. A spacecraft can rotate in infinitely many ways. Searching every possible orientation directly is computationally impossible. Instead, our system discretizes the entire rotation space using a Hopf fabrication grid. The module first identifies the nearest anchor, provides a course estimate, which becomes the starting point for a precise refinement. The 3D rotation exists on a curved mathematical self-manifold called SO3. Ordinary addition cannot accurately represent the movement on this surface. So, after identifying the nearest anchor, the system predicts only a small correction inside its tangent space using linear algebra. The correction is projected back on the curved rotation manifold, producing a highly accurate final pose estimate. But even an accurate prediction is dangerous if the AI does not know when it might be wrong. Thus, we have Jensen game gotch. Most AI systems give a single prediction and assume it is correct. Our system measures how reliable that prediction is. It analyzes 16 transformed versions of same observation and compares the results. Now see, if the predictions agree, the confidence is high. If they disagree, in a particular sun glare situation, the uncertainty is high. And that is captured using Jensen game metrics. Now let us understand how our AI actually reasons. For that, we have cognition agent. Let's discuss about it. Traditional AI relies on neural networks and often behaves like a black box. Our system uses hyperdimensional computing. Key concepts such as uncertainty, anomalies, confidence, and mission phases are encoded as 10,000 dimensional vectors. These vectors are matched against historical mission scenarios under a millisecond. Because every decision is made through vector operations, the system can trace exactly how it reached the conclusion. No black box, just fast, explainable reasoning. Now that uncertainty has been quantified, it must influence every decision that follows using the actions that it takes. So let's talk about action agent. So we have Monte Carlo digital twin for action agent. Before recommending any action, our system simulates 100 possible features. Each simulation starts from a slightly different state, reflecting real-world uncertainty. Some trajectories succeed, some fail, some collide. But what happens is every recommendation is backed by measurable outcomes and physics-based simulations. Not intuition, it's evidence. After this, let's talk about the orchestrator agent. The orchestrator agent is the agent that creates an environment for all these agents to collaborate and make sure that all the information is transferring perfectly via Redis pipeline. So, first of all, we can check that Redis orchestrator WebSocket and model all are loaded perfectly. Now, what we have is we are supposed to put some camera feed. The cameras are supposed to fed that are in and around the spaceship. So right now, for demo purposes, we can choose a file. Uh, The file is basically the image of a satellite that I have for demo. So over here, I can select this image of satellite and this is being analyzed. So right now, we are seeing an anomaly by the cognition agent and also an action. Right now, let's go for a particular scenario and we can try running this. Yeah, the system is running, the logs are being rolled, and what is happening over here is Jensen gain system is updated. The Jensen gain situation is being updated because of the image that we have been input. And see, the thermal failure and anomaly that we have been created has been detected by the cognition agent, and also action has been suggested by the action agent for that. Also, the Jensen gain, confidence, trustworthiness, everything is being told to us by perception agent. And orchestrator agent is perfectly aligning all the agents to make sure everything goes well. Now we can go for an explain command over here in the panel and we can get an entire explanation on what is happening, what should be done, and how the system is being running. So this is all about the explanation of our project. Thank you so much.